energy, power, watt, joule, exergy, thermodynamics. Welcome to watch the Sustainability Trends in Business. This time we will talk about energy. Energy is the key to sustainability transition. Many things can be created sustainably if there is enough energy available. Unfortunately, energy is not an easy concept to understand intuitively. Yes, we have some idea of energy, but when we talk about physics, it's much more complicated. And now we will have to take a dip into physics to make sure the basic concepts are understood. In case you slept through 3 years of high school physics, I try to go through the main points in 20 minutes. And don't worry, there are some things that are not emphasized in high school physics, and there are engineers who don't get all these points. The two main concepts to understand are energy and power. Energy is the capability of doing work, and power is how much energy is used in some time. So power is an instantaneous thing. It is something that happens right now. It's the effort. If I'm running very fast, I'm putting out a lot of power. So let's ponder this over a cup of tea. An electric kettle has a power of 2000 watts. It is used for 6 minutes, that is 0.1 hours, to boil water. Now by multiplying the power, that was 2 kilowatts or 2000 watts, by time, 0.1 hours, we get energy. In this case, 2000 multiplied by 0.1 equals to 200 watt hours. And please note that the units were also multiplied. This is important. So watts multiplied by hour is watt hours. So we use 200 watt hours or 0.2 kilowatt hours to boil the water. Energy can be expressed in really many units, but electricity is usually expressed in kilowatt hours or megawatt hours. As the numbers are large, it's not uncommon to sort of mix power and energy with each other. For example, have a confusion between gigawatts and gigawatt hours. But that's a big mistake, but easy to make. The official SI unit for power is watt. It's this guy here. And for energy, it's joule, this guy. A joule is equivalent to 1 watt for 1 second. So power of 1 watt for 1 second. That's a watt second, also known as a joule. As the energy needed for different things may vary a lot. And I mean a lot, really a lot. Prefixes are used to avoid writing a lot of zeros. Kilo, well that's the usual one for 1000, mega for million, that's 6 zeros, giga for billion, 9 zeros. But energy can use and uses tera, 12 zeros, peta, 15 zeros, or even exa, 18 zeros in the unit. It would be far too easy if everyone used joules. As said, kilowatt hour is a common one. 1000 watts for 3600 seconds, that is 3.6 million joules or 3.6 megajoules. Then we have calorie, which was originally the energy needed to heat 1 gram of water by 1 centigrade. So that's 4.19 joules. And of course, the Brits need to have their own BTU, British Thermal Unit, which is the energy needed to heat 1 pound of water by 1 Fahrenheit degree. And that is approximately 1055 joules. And then we have a very, very large thing, MTOE, megatons of oil equivalent, which is a lot, approximately 42 petajoules. And very unfortunately, these all are used, so sometimes you need to look up the conversion from somewhere. Just some examples. 1 terawatt hour is 3.6 petajoules, 1 kilocalorie is 4.19 kilojoules, which is about 1.16 watt hours. 1 petajoule is about 278 gigawatt hours, and 1 MTOE is 11.4 terawatt hours. Memorizing these is difficult. Use tables, use sources. Watt-hours are usually used with electricity, heat may use joules, and fuels use any of these. Here you can see some examples of orders of magnitude. First, let's take power. A mobile phone consumes about 1 watt in active use. If you sit still right now on a couch, your energy use is approximately 100 watts. An electric vehicle could use 100 kilowatts when accelerating pretty fast, and a jet airplane might be 10 megawatts. Large steel factories consume hundreds of megawatts, and largest single-site power plants are in the order of 10 to 20 gigawatts. And same kind of examples for energy. A tiny coin cell battery, you know, the flat little disc, may contain 1 watt-hour. Human beings' daily energy use is a couple of kilowatt hours, and a barrel of oil contains around 10 megawatt hours. Heating a municipal swimming pool may take 1 gigawatt hour per year, whereas a big ship can use hundreds of gigawatt hours per year. The electricity production of the largest power plant in the world, which is the Chinese Three Gorges Dam, is about 100 terawatt hours, roughly equivalent to Finnish total consumption. So the range is huge, both in power and energy, and human intuition is not that good with the numbers. With energy, it's not enough to understand how much. What is an important question. Energy comes in very many different forms. The most common form of energy is heat, which is actually movement of molecules bumping into each other. Then we have mechanical energy, which has 2 different forms. We have the potential energy. An example of that is if we lift a box onto a shelf, we need to do work. This work converts into potential energy as the box is higher up in the gravitational field. Another example, running uphill requires more energy than running downhill, because running uphill you are collecting potential energy, running downhill you use it. The other form of mechanical energy is kinetic energy, which comes from movement. Wind, for example, has kinetic energy as the air is moving. We have chemical energy, which comes in many forms. Fuels represent chemical energy. Burning them, that is, the reaction between a fuel and oxygen, releases heat. But batteries are another form of chemical energy. Batteries convert chemical energy into electricity, or electricity into chemical energy if they are rechargeable batteries. Then we have photochemical reactions, where chemical reactions release light, or photocatalytic reactions where light is needed for a reaction to occur. Electromagnetic radiation is about radio waves, light, gamma rays, and so on. And then we have electrical energy, which is something stored in electromagnetic fields, roughly called electricity. By the way, a funny thing, I'm a physicist, but if you ask me to define electricity, that's a very difficult task. And finally, energy bound to subatomic particles, nuclear energy, converting mass to energy. And here you can thank Mr. Einstein, who said that energy equals to mass multiplied by the speed of light squared. This classification into energy forms is of course a rather theoretical classification. A more practical way of solving the energy problems could be to have a look at something called primary energy. Primary energy could be called naturally occurring energy, so something that we can collect from the environment, something we can harvest. There are many forms of that. Fossil fuels and biofuels, they both are actually quite similar because both are results from some biological activity, and of course ultimately all biological activity comes from solar energy. Fossil fuels are just biofuels from 10 to 400 million years ago. Then we have hydropower, where we exploit water's potential energy. So we have water that is somewhere higher up and it's going downhill, and we extract energy out of that. So that's hydropower. The water cycle lifts water from the ocean, so it evaporates from the oceans and rains to the lakes higher up. This creates potential energy. Of course, the force behind this is sun, which heats the ocean so that something evaporates. Solar power can be used also directly by solar panels, for example, or solar heating. And then we have wind, which is air's kinetic energy. And again, why does air have kinetic energy? Is that we have airflows in the atmosphere, and these airflows come from the temperature differences which are caused by sun. So it's again solar energy in another form. Then we could use tidal energy, use the difference between low and high tides. This is actually primordial energy, as it comes from the kinetic energy of Earth and Moon. The Moon rotates around the Earth, which causes the tides, and this is something that has happened from the early days of the solar system, and there is no extra energy put into the rotation of the Moon. Nuclear energy comes from certain radioactive elements in the crust of the Earth, and they have been there, or sort of their precursors have been there since the formation of the Earth, which means that that is also primordial energy from the beginning of the solar system. Geothermal energy is a little bit sort of a half and half, depending on how it's harvested. If you drill deep down in the crust of the Earth in a place where you have volcanic activity, then you have volcanic heat, which is quite a lot of it is primordial heat. So from the days that Earth was a ball of molten stone, but part of it is actually maintained by the radioactive elements, so the nuclear reactions that are all the time going on beneath our feet. And then if you are extracting geothermal heat from the surface, close to the surface, it's mainly solar heat. So we have primordial, we have biological, which is sort of a complex way of using solar energy, and then we have solar energy. And with this introduction, we will come to the important part which people often get wrong. While all energy forms can be measured with the same units, for example joules, different forms of energy are not interchangeable. Apples and potatoes can be measured by kilograms, but one cannot make an apple pie with potatoes. This brings us to the very useful and quite seldom used term exergy. Exergy is a thermodynamical term, so mostly physicists use it. But what it really means is the potential of doing mechanical work with some amount of energy, or usefulness of energy. Physics says a lot about converting energy from one form to another. For example, the conversion of heat to mechanical work, which is very useful in power plants, is limited by the Carnot's law. The Carnot's law gives the maximum efficiency. Or, if we convert wind kinetic energy to mechanical movement, then there is something called Betz's law, which says that the efficiency cannot be more than 16 divided by 27, so about 2/3. On the other hand, the conversion between electricity and mechanical work is not limited by any fundamental rules. These limitations are of course fundamental in principle, but they are also important in practice. If we observe typical electricity generation methods, conversion from water potential energy, that is hydroelectric power, to electricity is over 90% even in practice. Very small losses. And best batteries, if we store electricity into batteries, best batteries have close to 100% efficiency in converting electricity into chemical energy and back. On the other hand, fuels are converted into electricity by burning and generating heat. And there the efficiency is, well, it's over 60% in the best case, but it depends on the fuel. Carnot's law limits this. In practice, wind turbines have efficiency of about 50%, not very far from Betzel's law. Nuclear power plants are poor, they have efficiency close to 1/3, which means that 2/3 of whatever comes out of the nuclear reaction goes as low temperature heat, which is quite useless. The efficiency is very poor due to the low temperatures in nuclear reactors, so the Carnot law again limits. Solar panels have 20% efficiency, which is far, far away from the theoretical efficiency, so there is a great opportunity for improvement. And then geothermal to electricity, basically you're drilling a deep hole into the ground and getting something like 200 centigrades out of it. That conversion to electricity is poor, it's about 10% or less due to very low temperatures. So the practical implication here, electricity is a good indicator of exergy, the amount of useful stuff you have in energy, because electricity can be converted into mechanical and back with almost 100% efficiency. So if you have a pile of coal and by burning it you get 1 megawatt hours, its exergy may be only half of it, because you cannot get 1 megawatt hour of electricity out of 1 megawatt hour of heat produced by coal. Or even worse, if you have lukewarm water, it may contain a lot of heat energy, but extracting it into useful mechanical energy is difficult. It's very difficult, so the exergy may be only a few % of the energy content. The very important message here is that different energy forms have different exergies. Physics textbooks start from the law of conservation of energy. And that's a useful one, yes. Whatever we do, energy remains. It may change its form though. And then again, a slight footnote, blame Mr. Einstein, but in some cases you can exchange energy with mass, but let's not worry about that here. So we have the conservation of energy. The conservation of energy is not that useful in thinking of the large energy sourcing problems. The principle of exergy is more practical one. Exergy is a slightly more pessimistic one, because whatever conversions you do, exergy can only be destroyed. In some cases you can keep it, but most of the time you'll just destroy it. These two are not in conflict because they talk about different things. In energy conversion, some energy is usually converted into heat. So the total amount of energy remains, but because heat, as we remember, has very low exergy, it's difficult to extract anything useful out of heat, then the total exergy goes down. And unfortunately, all energy tends to be transferred into heat in the end. So we are losing exergy all the time. Well, let's illustrate these principles with two energy-related examples. First, if we have a coal-fired power plant, a pile of coal has 1 megajoule of energy, and theoretically that could be 0.8 megajoules of exergy. Not 1.0, but 0.8. So less exergy than energy. In practice, we only get 0.4 megajoules of electricity out due to a lot of constraints. And this 0.4 megajoules, because it's electricity, of course it's the same amount in exergy, 0.4 megajoules of exergy. And then we get 0.6 megajoules of waste heat with almost no exergy left, because it's low temperature heat. Now let's see, the total energy is always 1.0 megajoules, the conservation of energy is honored, whereas exergy falls from the theoretical 0.8 megajoules to 0.4 megajoules. Both principles hold. A more complex but also very practical example is a ground-sourced heat pump. It's typical for heating modern homes. It is advertised to take 1 megajoules of electricity and give you 4 megajoules of heat out, which of course sounds a bit bad from the conservation of energy point of view, but it doesn't actually violate it. Let's see. We have the ground loop here. So there is liquid flowing in the ground loop, and we are collecting energy from the ground. Yes, that's very low temperature energy, but it's still energy. So if we have 1 megajoules of electricity in and 3 megajoules from the collection loop in, it's 4 megajoules out and nothing is violated. Great. We take 1 megajoules of exergy in because, as we remember, electricity is such that energy equals to exergy. And then we can take very, very little exergy from the ground because the temperature difference is so small. We can see that we output 4 megajoules of heat, but heat has very little exergy, so maybe it's only 0.5 megajoules of exergy in there. And now if we add everything up, we see that we get 1 megajoules of exergy in, 0.5 out. Loss of exergy is honored, and we get 4 megajoules of energy in, 4 megajoules out. Again, this works. One important feature in exergy is that whenever there is a loss of exergy, we are not at the theoretical upper limit of efficiency because, of course, the definition of exergy is such that it's maintained when we have an optimal process. Things can be done better. Sometimes it's very difficult in practice, but sometimes it's not. Okay, I understand all this might be a bit confusing, so just remember to keep energy and power apart. Understand some of the units, understand that there are many of the units just to make your life more difficult. And please remember, different energy sources have very different amounts of useful energy in them. The next episode will be about where we really get our energy and where we use it. A lot more practical stuff. Thank you very much for watching. See you.